Our study of projectile motion is going to use our understanding of vector components, and it's going to build on a lot of our understanding of Zuvat equations. So before you start this, make sure you're very clear on how vectors can be broken up into horizontal and vertical components, and about how the x, u, v, a, t constant acceleration formulas work. So a projectile is defined as something that flies through the air without a thrust force pushing it. A rocket or something has a thrust, so it's not a projectile. A bullet or a javelin or something that's thrown counts as a projectile because it has no thrust. It's initially provided some force to give it some kinetic energy, but there's nothing pushing it through the air as it flies. So the only force that acts on a projectile is gravitational force, which is of course vertically straight down. For our purposes, we ignore air resistance in calculations. You need to be able to discuss what effect air resistance would have on the results of your calculations, but you never need to factor in air resistance into your calculations. So here's an example to start off with. We're standing at the top of a 12-metre cliff, and a ball is dropped vertically down 12 metres, and we're asked to find how long it takes to reach the bottom. So as with all our Zuvat equations, what we're going to do first is list the things that we know. So we know that x is 12 metres. I'm going to define downwards as positive in this situation. We know that the acceleration vertically is 10 metres per second squared. And we know that since it is dropped, that u will equal 0. And we're asked to find t. So the equation that we're going to use here, x equals ut plus 1/2 at squared. And so putting in what we know, 12, this ut term goes to 0. We get 1/2 times 10 times t squared. And so t works out to be the square root of 12 and 5. Close enough to 1.55 seconds. So that's how long it takes for that ball to be dropped to hit the ground from 12 metres high, assuming no air resistance, of course. Okay, this time we're asked to consider a ball that's been hit horizontally from the top of the cliff. It's moving at 50 metres per second horizontally. We're asked to consider how long it takes to hit the ground. We're also going to be able to work out how far it travels before it hits the ground. So, because that ball is going to follow some sort of parabolic path through the air, it's going to have motion in both horizontal and vertical directions. So what we're going to do is actually split that up. We're going to split up our thinking about this ball into its horizontal and its vertical motion. So horizontally and vertically. So horizontally, its initial velocity is 50 meters per second, and vertically, its initial velocity is 0. Acceleration, I'm going to define downwards as positive again. So acceleration is 10 vertically. And thinking about the acceleration horizontally for a moment, acceleration comes from a force. So there needs to be a force for there to be an acceleration. But there is no force acting horizontally on a projectile in flight, assuming, of course, we're ignoring air resistance. There is some force being applied to the ball, an impulse at the start of its motion, but when it's flying through the air, there is no horizontal force acting on it whatsoever. So, and this is a very important point here, acceleration horizontally is 0. We know that the distance it travels vertically, its vertical displacement, is 12, and so we have enough information in this part, the vertical component, to calculate the time it spends in the air. So by using our same equation, x equals ut plus 1/2 at squared, you'll see that all of these quantities are exactly the same as what we used before. and so we will get exactly the same answer, that t equals 1.55 seconds. So you may have seen that Mythbusters episode, or you may have heard this told to you in a science class before, that an object that's dropped and an object that's fired horizontally will hit the ground at the same time. So if this ball was hit at the same time as another ball was dropped from this cliff, they would both hit the ground at the same time. Obviously the one that's dropped will hit somewhere here, the one that's hit will hit somewhere out here. But because their vertical velocity is exactly the same, their vertical motion is identical, the vertical component doesn't change whether it's dropped or whether it's hit, they will hit at exactly the same time. Now, suppose we want to figure out exactly how far from the base of the cliff this ball will land. Well, what we can do with this time is one of the few components of motion that can actually transfer across. So, because the motion through the air is the same, the time will be the same because it's the same object travelling the same path. So the time horizontally will be the same as the time vertically, and that's a very useful trick to link the horizontal and the vertical components together, is to use time. So now we're going to work out x, the displacement horizontally. So we're going to use the same equation, x equals ut plus 1/2 at squared. But luckily for us, acceleration is 0, and so this term here goes to 0. And so what we're left with is x equals 50 times 1.55. And so we can see that the ball will land 77.5 meters from where it started. That was its horizontal displacement. So the things we need to remember are that horizontally speaking, acceleration is 0, and vertically it's equal to gravity, and that the time can often be used to connect the horizontal and the vertical components of motion together. We'll have a look at some more complicated questions in future videos.